So this meeting, I read the purpose of the meeting, and I was trying to figure out why I was here. Okay, I liked the idea. We're going to bring together people. Oops, I guess I need to. Well, I don't have a pointer. Does this pointer work?
That's it.
Yeah, okay. So what I did, of course, was look up what's a pioneer, and so I Googled it, and they're not going to work. I have to do both of them.
No, I think that works for both.
This works? No, my stick is in there. Okay. That's okay. That's okay. So I can use both hands. Very good. This is the definition if you look up what you find in Pioneer. Pioneer species is a hardy organism that has to be small, simple, and capable of producing their own food. Okay? And I have at least two of those three traits. I'm pretty simple, and I'm not real small, but I can produce my own food. Then I remembered about another pioneering group, so-called Donner Party. That was a group of American pioneers, and I'm sure that some of the students here don't know. But so I have to give you a trigger warning. That was a group of pioneers. And that group wound up lost, cold, and eating each other. So I'm going to try to avoid, I'm going to be lost most of the time, and I just don't want to have you throw me outside. Okay. Here are the people that do know what they're talking about that I work with, and optimization and control, and they do all the work, and I get to come here and give the presentation. That's the way it works. I'm not a pioneer in either or two, but the one thing that I do have is problems. I don't know how to solve them, but I have lots of problems. And so I'm sort of putting this out as a class of problems that you might be interested in. Right now, I'm sort of interested in sort of environmental control systems for airplanes or HVAC for your house, and in general, aircraft thermal management system. And these things have basically become a limiting factor in a lot of the modern fighter jets, the F-22 and the F-35 in particular. These are severe problems. So we'll talk about what a thermal management system is in a little bit. But before I do that, I mentioned on the slide something about small parameters. So I want to talk about small parameters. I'm sort of at heart a dynamical systems person, controls person, so I'm going to give a simple example. And here's my question. Suppose I got a dynamical system, which we typically write as x dot is a, well, I guess z dot is az plus f, got some nonlinear, linear part, and we have two kinds of parameters here. We're going to have parameters in blue, so things are color-coded so later they'll make sense, and parameters in red. And what I want you to do is think of the blue parameters as small for a moment. Okay. And then we're going to discretize the system. And if that's an ODE, you'd probably use something like a discrete approximation, and you produce a discrete dynamical system. I want you to think of it that way. So we're going to do a discrete version of this dynamical system. That's the dynamical system. So now we just got an iterative map. Again, it depends upon the parameters of the system, and we give an initial condition, and we iterate the map. That provides a semigroup, discrete semigroup, on the space 2. So there's a question, simple question. Suppose that I got a point in the omega limit set of this dynamical system. So I'm going to worry about the long-term asymptotics. So what does that mean? That means that there's a sequence of times so that you start at z0, the semigroup's going to take you to that point. What happens at the discrete semigroup? So for a small delta t, does the sort of omega limit set for a particular point, is it the same as the omega limit set there or close? So that would just mean if we iterate the map, do we also get the omega limit set? So in general, the question is you got some long-term behavior, global attractors, asymptotic properties, and you're going to discretize the system, and you'd like to know, do I preserve that kind of asymptotic properties? The answer to these in general is very hard, and in general, no. So that's why we're going to do an example. So you'd like to also know the converse. If you got sort of an approximating system and you know something about the asymptotics, can you conclude something about the asymptotics of your original system. So you don't have to get very difficult. I like simple examples. And here's the one that's real simple. A is a positive number, and we just look at a little ODE. Z dot is minus A, Z cubed. We give it an initial condition. We can solve this directly. Everybody can do this. And it's clear that no matter what the initial condition is, the limit's going to go to 0. So what does that mean? That means the mega limit set for any point is 0, which basically also means 0 is the global attractor. Okay. So the question then, suppose I do something like, and note I'm going to take H, you can think of as a mesh size, or in this case it's a delta T, and I'm going to take a uniform 1 over n. It's going to be important later. So we discretize this problem, and we'll get a discrete dynamical system, and I want to know if I have the same initial condition starting here, am I going to capture the same global attractor? Okay. So what's the system? We'll do what everybody knows, Euler's method. That works, right? We know that if I use Euler's method, it turns out looking like this. And we want to know, there's our discrete map, there's our discrete dynamical system, and we want to know, does this capture the same asymptotic as this? Okay. So we're going to give you an example. Let's let Z naught be 4, and what happens, and you kind of guess. Here's a plot. The green line, I hope you can see, is the actual solution. It's at 1 over the square root. The red line is what happens if you take delta t sufficiently small, and that's it. And if you take it smaller than what I gave you for the red line, it'll eventually become monotone. Okay. And this line here, I didn't plot, it basically oscillates back and forth between 4, minus 4, 4, minus 4. And if you're unfortunate enough to pick the step size to be exactly that value, and if you pick the step size bigger than that value, the solutions blow up. So we can summarize this really quickly. As long as you've got delta t times A times the initial condition squared less than 2, you got that the mega limit set for that initial condition is the 0. It's the right mega limit set. And otherwise, you don't. Okay? You get sort of oscillating behavior or no limit set whatsoever. So that looks good. You can prove that. I have a theorem. So earlier Margaret talks about proving things and not proving things. So what we managed to prove is if we do forward Euler, at least for some, as long as we take this parameter, delta t small, then you're okay. But actually delta t times A small. So think of A being small. That means you can take a step size as large. That's a good thing, right? Okay. We're going to theory. We know that if I take delta t times A times the norm of the initial condition less than 2, then this is going to converge to 0. Now let's compute. Let's make an assumption that that's really small. If this value is less than machine epsilon, which on my laptop it's that, what happens when you compute? Well, that's certainly less than 2, so the theory tells you that this sequence is going to converge to 0. What happens? Well, let's think about it, what that means to say that this is less than machine epsilon. So here's the map. You start out with Z naught, which is 4, and Z1 is going to be that. It's 4 times this. But wait a minute. If delta t times A times 16 is less than machine epsilon, then the computer is going to return machine epsilon, which is going to give you 4. And then Z2 will give me 4 because machine epsilon, 1 plus machine epsilon is just 1. So what we find is we don't get the right answer, right? It's a function of finite precision arithmetic. It's not round-off error, by the way. It's finite precision arithmetic. And I'm going to just raise that as a flag right now. We'll come back to it later. So your first question should be, well, nobody would use OR, right? Let's use a better method. Let's use backward OR. So we can do backward Euler. And you're right, the theory gets better because you can actually estimate and find out the sequence of iterates are decreasing. And you can prove more than that. You can actually prove they actually converge to 0 for any initial condition and any delta t and all A. That's great. That says if I use this dynamical system described by backward Euler, then what I'll get is exactly the same global attractor. But that looks good. but we're still going to have a computational problem. If this ever gets less than machine epsilon, you're just going to return whatever you started with. Okay. So you might think that this is a good thing, and let's think about what we need to have. We need to have delta T A times whatever the norm, the initial condition squared, bigger than machine epsilon, or else the machine is going to produce the wrong result. And you might say, well, that can never happen. This is a nice mathematical problem that's made up, counterexample. I just want to point out that this says that if I take delta T and keep refining, what the theory would say, I'm going to get in trouble. Or if A is small to start with, I'm going to get in trouble. Okay? Going to get the wrong answers, asymptotically. Red flag. So you're probably saying, can't happen. Let's look at a problem that looks a little bit more physical. Okay? This is Berger's equation. That's not the type of thing that people usually play with Berger's equation. It's Berger's equation, and I've got a Dirichlet boundary condition on the right and a Norman boundary condition on the left, and it's equal to minus A. And again, I want you to think of minus A as a small value. Okay? So mu is sort of positive, A is a small value, and we could ask ourselves, basically, if I let A be 0, we get this problem, which is well studied. Right? It's just a Berger's equation with zero flux at the left and pin down at the right. Generates a dynamical system for any mu, any A. Okay? And you can prove the following. There's a theorem. Even when A is 0, or A is greater than 0, when A is 0, this has an equilibrium, namely 0, because you solve this two-point boundary value problem. The only solution, primarily because of that, is 0. Not only that, it's a little harder to prove. It's amazing how hard it is to prove. But about a few years ago, you can prove that this dynamical system is asymptotically stable. All solutions converge to 0 globally, which means, again, 0 is a global attractor. Okay? So all the theory is there. That's really nice. This first proven by Gilliam and Schuboff in 1999, so it's not 100 years old. But what happens? Nothing seems to be amazing, so I'm going to solve this problem right here. I gave it an initial condition, just a straight line, and you use a standard finite element, and look, it goes to 0 just like the theory said. That's great. That's the kind of thing we like to see. Theory and computation match. So what happens, though, is what if I change this initial condition just a little bit? Nothing should change theoretically. All solutions should go to 0. That's what the theorem says. But this is what happens. If I just make the initial condition just slightly larger, and note that's time marching out, it doesn't go to 0. In fact, it'll sit there, right there. Okay. And you might say, well, I used a bad approximation. We're going to talk about that in a minute. The question is, what's wrong? That's not what the theorem says. Contradicts the theorem. So what's wrong? And what is this curve here? Well, it turns out, after a lot of pain, you can figure out exactly what that curve is. That is a solution to this steady state problem where A is a number less than 0. Okay? So this is a solution to the steady state problem where this is just bumped up to a slightly off 0 number. Okay? So actually, this is the steady state solution of this problem here. But I want to tell you what we implemented was the previous problem with that 0. Okay? So what went wrong? So it must be the A that I used to do that's big, right? It's not big. But machine epsilon will do it. And in fact, after a lot of work, you can actually prove this phenomenon occurs because you're computing on, again, a digital computer with finite arithmetic. And you can actually describe what this curve is. It's a hyperbolic tangent. This alpha depends upon the mu and that A. And it doesn't really matter, if you're going to get that false solution, which method you pick. In fact, if you pick a convergent, stable numerical scheme, you're guaranteed to produce the wrong answer. You can prove that. Okay? So pick your favorite scheme. I used to have arguments with a guy named Max Gunsberger, a fundamental guy, and he tried about 25 times to fix this. You can't fix it. It's fundamentally a problem with finite precision arithmetic. Okay, and we didn't make up the problem. I have a graduate student that won't talk to me right now because he was doing a control problem here, and he would do the open loop, closed loop. The open loop was with the 0, and he kept getting the wrong answer. I made him look at his code. I told him it was wrong. Some 10 years later, I had to try to find him and apologize to him, but he still won't talk to me. Okay, so the point is about all of this, this false solution is basically a solution to a nearby problem, but it's very sensitive. So sensitive that if you don't do things right, you're going to get the wrong asymptotic answer. Okay, now you might wonder what this has to do with the theme of the talk, but we're going to come back to that. Because we're going to talk about where we ignore small parameters, and you can see you can actually cause big problems. Okay, this is the problem that motivates what we want to do. This is a slide I got from people at the Air Force, and they're talking about the next gen fighter jet. And modern fighter jets, F-22 and F-35, all use a vapor compression system to cool the airplane. It's a stealth plane. You can't just dump heat arbitrarily. So it actually dumps heat into the fuel. So it's flying along, all the heat generated by the inside, the electronics bay, there's a heat exchanger, dumps it in the fuel, and you get the heat out of the airplane when you burn it. Very clever idea. Call it. And basically it's a thermal management system that does this. And they model this, and they tried to design a controller. And the big problem is the dynamic model of the heat exchangers that they use on the airplanes. That's a modeling problem. It's a calibration problem. It's a parameter estimation problem. Okay. All right. Is it a big problem? This is another slide, and this is how big it is. It's limiting the mission of the F-22 and F-35. For example, in the F-22 now, if they're flying in the Middle East, they have to take the fuel trucks. They're all painted white because they've got to keep the fuel very cold, and then they have to fuel up the airplane to take off because they're dumping their heat into the fuel, and it limits the mission. So it's a serious problem. I mean, you probably heard about a month and a half ago, they grounded a couple of F-35s because of the thermal management system. And I like this. This is sort of a whack-a-mole problem. If you fix the problem here, it shows up there. But they're trying to design better heat exchangers. They're trying to understand how to sort of control problems, how they manage the control, heat the fuel, pump it around. That's a big problem. Is it a problem? This is the heat exchangers. That's the F-22. And the next pictures are real pictures. Known cause is failure of the thermal fluid management system. And that's what it looks like. And that's what that looks like. And by the way, they've lost more of these due to problem with exchange of heat than they've lost by being shot down or anything else in the last few years. Okay, so what is this system? It's a vapor compression system, and it's very simple. They have fuel that's cold, and you want to dump hot into the cold, into the fuel. So you have a simple vapor compression system. It's real simple. The hot air, say, comes in here. The cold fuel comes in, well, inside you've got a refrigerant, that's what this is. The fuel is, you've got a heat exchanger that takes from the heat from basically here and dumps it into there. You control the compressor, the expansion valves, and there's actually control motors back there. But this is what the system looks like in general. These are the heat exchangers which are causing most of the problems. And the big problem is how can they model these, and dynamic models are needed. Okay, that's motivating a lot of stuff that I've been interested in. And basically the models are very bad. That's just a simple way to put it. They're pretty bad. Why are they bad? What's causing problems? The first one, the models fail at low or zero flows. They're not dynamically very fast. Okay. And here's the ones I'm going to focus on for today. I really would like to talk about control, but I'll talk about this one today. There are 100 parameters in these models, sometimes 1,000. The models that are being used currently are simple reduced ODE models. When I say reduced, it's not reduced order modeling. It's pretty crude approximation of the physics. We need a small model. There's a lot of things that are needed, and Well, better physics, we need actuator dynamics, but I'm going to focus on these three. You need to talk about the approximations, and we need to talk about how we get models, because we're going to need them for different reasons, one for control, one for design, and we basically have to do some parameter calibration and estimation. There's a lot of other things that are important here, but I'll just sort of talk to these 3 or 4 points. There are small parameters. Okay, this is going to fail because of a small parameter. I'm not going to describe it in a simple case. Again, the people are interested in the United Technology Corporation we work with, they own Carrier Air Conditioner, they own UTAS. Larry Bigler and I have worked on these problems for a long time. And these are big air conditioners, 2 on the 787. That thing will cool about 25 houses, okay? And if both of those fail, the 787 sort of falls out of the sky. So you may not want to know that next time you get on one, but it does. All right, so what are these things? You look at them, you can see pumps and electrical valves, and you've got compressors, you've got fluid flow going through these things. So basically, you got all sorts of PDEs, DAEs, everything combined. It's a very complicated system. And realize if any one of these components is infinite dimensional, so you got fluid flow, the whole system is infinite dimensional. We're going to have to approximate something. Okay. The heat exchanger, again, is a critical technology in approximating and modeling these things. It's not trivial. I'm going to do a trivial example. See, I like trivial examples to try to figure out what's going wrong with the most important thing. So here's a simple explanation of what a heat exchanger is. This is what's called a counterflow heat exchanger. So think about, in the outer pipe, you got hot fluid going this way, and in the inner pipe, you got cold fluid going this way. And so you have heat exchange from hot to cold, so the cold fluid gets heated and the hot fluid gets chilled down. Okay, it's very simple. Now, heat exchangers obviously depend upon space, and this assumption is made in 99% of all the models. Namely, which is true, it is the convective flow rate that is the most important mechanism for heat transfer. And diffusion, okay, is small, actual diffusion. So let's just throw that small term away. That's the argument. What happens when you do that? And how is it going to impact what we're about to do? So let's look at a simple model of a heat exchanger. You can find this in the literature. It's sort of a standard one. So you got the temperature, hot going left to right, cold going right to left. The hot heats up through the wall, heats up this. So this is a simple model of the coupled system. This is the diffusion coefficients. These are the velocities. You know, this is going from left to right, that's going right to left. These are the heat transfer coefficients. And I'm going to give examples where we'll assume that the hot fluid is coming in at 100, the cold's coming in at 20. And note that I've got this little thing there. Maybe there's some disturbance in there. It's blue, one of those blue things. It might be small. These things are controlled, and for the problems that we're really trying to do, these parameters will actually be controls too. But for right now, I want you to consider that little blue thing as an unmodeled disturbance. Okay. Now, we're going to set up a problem where it's typical to say this is much smaller than this, so it's convective dominated, so we're just going to throw those parts away. And we wind up with a simple two-coupled hyperbolic PDEs. So, in essence, that gets done in 98% of all the models. So we're going to give an initial data that sort of matches the boundary conditions. We're going to measure some outputs that we're going to use to try to estimate, say, the heat transfer coefficients in this little simple example. And we're going to assume we've got some sort of measurements. We're going to measure the temperature of the hot fluid as it leaves the pipe and the temperature of the cold fluid as it's leaving the pipe. Those are our measures. And of course, we're going to have noisy measurements. So in that framework, there's our problem. And if we assume, it is a modeling error to assume those two things are actually zero. Think of the Burgers equation. We assume that boundary condition is actually zero. Now, if we do that, then I'm going to change the color of my, these parameters are going to be blue. They're really there. It's there in the physics. Every fluid has some diffusion capability. It can be very tiny, especially compared to the velocities. But we're going to leave it in there for the moment, okay? These are small, unmodeled parameters, okay? But they're small. What can that hurt? So again, we're going to do an identification problem where we're going to fix the velocities and try to estimate the two heat transfer coefficients. And we're going to consider the case where A is actually there. A is the forcing the disturbance plus the small diffusion coefficients. And the question is, what possibly could go wrong? Okay. So our measured output, now again, A, this is a model that just takes and measures the temperature at the outflows of both pipes. It depends upon those coefficients. Now when they're zero, that would just be zero. That's assuming that all those things are gone. And that's sort of a true model, the best we got. So we know something about it. That's really there. So a little bit of notation. If I write mu is greater than zero, I mean both of these things are greater than zero, and we know they are. And what happens is, if A is not zero, then you've got a parabolic PDE. But as soon as these things are zero, you've got a hyperbolic. You have a singular perturbation of the system. Okay. This is the model when they do the real physics, the full nonlinear, in essence they're dealing with. It's a hyperbolic system. And it's a singular perturbation of that. Okay? So we're going to take as an assumption, that's our model, and we're going to take data, and again, I'm just going to fix these so we can set those because that's a control. We want to estimate those parameters. How well can we do and what should we do? So this is something that we know is true. We're assuming the output to our model is given by G naught. We don't know that there's an A naught, and we got some noise. But basically, we know there's something wrong with the model discrepancy. You add a term called the discrepancy or the bias. And what we need to do is estimate not only this parameter, we're going to estimate the bias of the model discrepancy. Okay. I want to point out that that has at least two parts. I hate to use these words, but we can break it down to something called what I call the known unknown. We know in the model that's not zero. It may be small, but it's not zero. And then there's the other thing, which is the hard part, so I avoid that, is sort of the unknown unknowns. You don't know what else is in the model. When you do experiment, there's actual things that are being modeled, but you can't model them. So the people that really know what they're doing in model discrepancy just try to find this whole kit and caboodle. For example, one way to think of this is delta A is just the true model minus the assumed model. That would be one way to think about it, and it's often thought about in those ways, but you still have a lot of discrepancy in the model. So, there are a lot of powerful Bayesian methods to deal with this statistically. I'm not one of them, okay? Although there's some very interesting papers out there that's going to give you a hint about what you should do in this. The model discrepancy, again, I want to break it up this way. It's normally not done. But you do have some information about the discrepancy. And you really want to know the whole kit and caboodle if you're going to really estimate the parameters and not generate a biased estimate. So how do? You assume in a model, this is model-based design, you assume you've got fixed parameters, you generate data, collect the data at a finite number of times, and you're going to do least squares, maximum likelihood, it doesn't matter, but it's going to be an optimization problem. So we got data, which is actually generated from the true model, plus some noise at discrete times. And the goal is to estimate that from the measurements, noisy measurements. So here's the question. If I break it up like this, can this information right here help me improve the sort of parameterization or the representation of the model discrepancy? And the answer is yes. Okay. Not my idea. This is a very nice little paper that appeared a few years ago, and O'Hagan and Kennedy were the ones that sort of started this whole thing about model discrepancy. I would love to know how to pronounce that name, but it's never going to happen. Okay. This is a really elegant paper. Okay. So if you read this paper, you find a couple of comments, what they find. If model discrepancy is ignored, then predictions, interpolations are going to be bad. Okay? What's even more interesting, if you sort of don't do it well, the more observations you get, the worse you are. You can be more and more sure that you're getting the wrong answer. It's a really nice paper. They got nice examples in there. I'll show you one. If you model the model discrepancy as sort of too simple, then you're going to still get biased estimates. And this is a key if you want to get realistic method for learning about the physical parameters, as well as we'll see things called hyperparameters. Then you got to be very careful how you model that discrepancy. Okay. But they did point out that, gee, if you use physics, in this case for me, physics is going to be dynamics, to increase prior information about this. And the one thing they didn't talk about, which is important to me right now, is you got to understand that some of these parameters are small. And you've already seen that sometimes that can bite you just in the simulation. Okay. So for example, we know that mu in our heat exchanger model is strictly, in other words, it's very small, but it's there. Okay. Engineers would say, throw it away. Small. Okay. We sort of expect that the disturbance is sort of randomly distributed on some sort of interval. So that's a statistical kind of thing. And the challenge is still a challenge today. Develop good priors on the model discrepancy term so that you get away from some of these problems. That's the challenge. Now that's way above my pay scale. Very challenging problem. But I'm going to give you some insight that they have in this paper. Basically, simple examples tell you a lot. First simple example is this one. You'll find it here. So your model is just Q times T. It's just a linear model, but you've got this sort of damping term. It bends over, and that's considered unmodeled. And they use exactly this example in this paper to, I don't know why it keeps going the other way. They set parameters they want to estimate. They make that small. And you can tell a lot about the discrepancy because you can actually compute it here. You know what it is. You know at time equals 0, it has to be 0. You know that the derivative has to be 0 because you want to capture the right parameter. They also noted some other things. You have some monotonicity in this. So what they did was take advantage of that later to build the priors on the model discrepancy term. I'll show you in a minute. I first got interested in this actually in this paper by Jim Berger and this group, where they had a much simpler model. Can't get easier than this. They didn't write it this way, but the model was x dot is qx plus a, x at 0 is 5, and they wanted to estimate q. That was considered unmodeled and small. Okay. So the values that they have, just so you know, it's not small in the numbers they presented, but that's the value. That's the true value of the model. And you can look at it, you can figure out, so as you'll see in a minute, what they did, get the same property. The model discrepancy, the known model discrepancy has got to be 0, it's got to be monotone, and you can get boundedness on the model discrepancy, you can get precise bounds on them. Okay. So let's go back, let's continue to look at this. What do I mean by get information? There's the model, again, small but unmodeled. And if you write out the solution, of course the variation of parameters formula tells you what the solution is. And you've got, again, error for the measurements. But this right here is basically the known model discrepancy. If you know there's an A there, no matter how small, that's it. You still got some unknown model discrepancy. So that's it. It tells you lots of things. You find out, like I said, it has to be 0 at 0. You found out the derivative has to be whatever. Don't preference the sign in this. But this is the one that I kind of like. You know that the sort of known model discrepancy, that part of it, has to asymptotically converge to that value. Okay. Just properties. Just comes from the dynamics. The structure comes from known physics, both in both papers. You need to somehow parameterize this model discrepancy if you don't know what it is. And for example, here it's clear. The right parameterization of this is just exponential polynomial. Not only that, because we've got this thing is 0 here, we know that B naught's got to be the negative of B1. Okay? Use that information. Like I say, many approaches. If you look at this paper and you look at Jim's paper, you find out, well, they sort of take data, they do sort of a basically a Gaussian process, Kriging kind of ideas. And so you assume there's a distribution on your model discrepancy, And then you've got a couple other parameters to estimate. These are called hyperparameters. Okay. And in this paper, they did something else. They used those constraints of prior information about the physics to produce what they call a constrained Gaussian process model. Okay? So you use information like this. They did. This makes it a little more hard, but you can use this kind of information. You place constraints on your Gaussian process, and they call it a constrained Gaussian process, the Bayesian methods. And this is a nice result from the paper to show you the benefits. If you have no model discrepancy, then, and this is, they did 11, 31, 61 observations. There's the true value of the, I call it Q, but it's theta. And this points out with no model discrepancy, you're way off. And the more data points you pick, you're more confident that you're way off. Okay? And by using what you would find in sort of the literature, a standard Gaussian process, it's, well, at least you got some tails here. But if you use the constrained Gaussian process prior on the model discrepancy, much better. There's lots of plots in here, but that's just sort of the theme, okay, using these constraints. This one is the interesting one for me. Look what they plotted. They've got the posterior information about that is the actual model discrepancy. Note they took data 0 to 4, so this is outside their data, they're trying to predict. And the posterior mean of the model discrepancy, whoop, goes there, and you have no information that's valid out there. So what you need, and the paper, I'm just quoting from this paper, is you need to have realistic prior information coming from physics, but you've got to have prior information in the range of the data, which is typical, and you need to have some idea what the model discrepancy is outside the range of the data. Take into account the long-term behavior, for example, of the dynamical system. Okay. So, I'm going to now switch gears, and let's just do another approach. Another way to think about it is we're going to take these two things, lump them together, and we're going to approximate this by some expansion. Okay, so the model discrepancy, this is to be approximating both this and this. And we're going to take some sort of functions, delta k's, write a finite number of sums, and if we know this, what these things are, that gives us n hyperparameters that we also have to estimate. Okay? This is also done in this literature. We need to determine the form of these things. Again, you would go back and use that information like you find in the previous papers. You could do something, and believe it or not, some of us dummies have done this. Let's think about doing a Taylor series approximation of this. If you don't know anything about it, why not? Well, it's not going to be good for long-time prediction because, this is going to blow up. Or you might do something like this. Assume that this has this form. Why in the world would it do that? This is exponential polynomials. So note, I got a lot more hyperparameters here, right? I got actually 8 in this model. And say, why would I do that? We do this because we know something about dynamics. If we know that the system has a decay rate, that's a negative number, we know that this needs to somehow match the decay rate. Okay, I'll show you what happens. Well, we did this. We applied it to a bunch of problems, started a couple of years ago, and applied it to this problem. This is an interesting problem. It's a delay equation. R is one of those things you assume is there. It's really there. A is a disturbance. And if R is positive, you've got a delay differential equation. In fact, it's infinite dimensional, and all the solutions can be written as a series of exponential polynomials. That makes good sense. I want to point out that if R becomes 0, then A0 and A1 are not identifiable. Okay. But if R is positive, they are. And in fact, this is, again, it generates an infinite dimensional dynamical system. So then, well, we had a lot of success with that. We thought we did. So we thought we can do tougher problems than that. So we played with this little problem, which turns out a lot of people play with this. So think of it as a logistics equation when A is 0. If A is not, it's called the population dynamics with Alley effect. And you got certain bounds. I'm going to emphasize we're going to wind up with constrained optimization problems. And we know that A could be 0, which recovers the logistic equation, and A, we're going to have to just keep it less than 1 because otherwise you go through a bifurcation and you're in big trouble. Okay. So we took this kind of thing, we applied it to this, and wow, we got all these parameters. It looks terrible. Certainly it can't be identifiable. Here there's absolutely no problem because this is an infinite dimensional system. But it turns out you can use prior information again about your dynamics. For example, using this kind of information, you plug it in. If you were to assume an exponential polynomial, then you got some constraints. So, these aren't all independent, and you should use that. You should. Okay. Suppose you don't, and we'll see what happens. So here's the problem. We got two kinds of problem. I could call this a parameterized model form. Somehow we parameterize the model by this a caret, and then we're going to assume a model discrepancy. It's like an exponential polynomial. And then we want to basically solve two problems. Find the parameter and actually find the model. That's what that says, to minimize a least squares fit to data. Okay? Later, that's going to get a little bit more complicated. If we assume we got some sort of model discrepancy of this form here, then we can solve what's called the structured model discrepancy. It's not arbitrary. There's some structure to the model discrepancy term, and that's similar to what the people, Kennedy did. And we want to find Q and H, the hyperparameters. Note, we're not looking for A because it's not there in the model. The hypothesis is it's not there. 0, gone. So what if we solve these two problems? Well, we did the same thing for that. We did the same thing for that. But now we're trying to do it for this, okay? And this is where things get interesting. Okay, we're trying to estimate the parameters K1, K2 from measurements taken. And we know some things. We know that the disturbance has got some bounds on it. We know that the mu i's are sort of max or strictly small, but they could be 0, but as far as the model is concerned, we just assume they're small. We know they're positive. And then we got some bounds on the flow rates and the heat transfer coefficient. There's two additional things that happen. So one you already know about that causes a problem. One is, I can write this. I like writing everything. Used to write Z dot is AZ plus BU. I'm a controls person. A has 3 parts: a parabolic part, a hyperbolic part, and sort of a bounded part. And these, if we assume that there is no diffusion, then you wind up going from a parabolic PD to a hyperbolic PD. And some interesting questions. Can you actually prove, as mu goes to 0, that these two systems, the dynamical systems, match? Can you prove they have the same asymptotic behavior? Not quite the same. There's some damping rates that change. So we've got to approximate this no matter what. Okay? And you can try your finding elements, finding difference, don't care what you like. But just like the simple example, Z dot is minus AZ cubed, you could use forward difference, or say finite elements. You could use a backward difference, a finite volume. But in a sense, you're going to do something. You're going to get a mesh size on the pipe. Now this represents a mesh size. We're going to generate a finite dimensional problem. And they're going to be ODEs now. And hopefully it's got the same structure as this. So the N now represents sort of the dimension of the system. Okay. Big N, big dimension, small mesh. Okay. So now then we needn't worry about how we do this. Why do we need to worry about how to do this? Because we like to know, again, if mu is not there, do we capture the hyperbolic system? So it turns out, if you take this part of the equations, that's this is a parabolic differential operator. It's self-adjoint. That's a good thing. These first order terms are hyperbolic, and they're not self-adjoint. In fact, they're very far away from being normal operators. And so it says, well, maybe what's great about finite elements and finite volumes, if you've got a finite element scheme, it's really good at doing self-adjoint parabolic operators, not so good at doing hyperbolic. So there's all sorts of mechanisms, upwinding and all this, to deal with this. But there's a really nice paper that appeared a couple of years ago where they called what's called a combined finite element, finite volume discretization. And this is what we got, convection diffusion equation. And it's L2, stable, numerically stable, independent of diffusion. So theoretically, what happens is, if this goes to 0, you capture the hyperbolic problem. It's not quite just upwinding, it's not this, it's a very special thing. But you can apply it to these little, this is one spatial dimension, it's easy to do, that's why I do it. Remember, A is there. We know that mu is really greater than 0 in the real physics, but we would like to be able to capture the right even if it is 0. That's my small parameter. So we go from this problem, use this combined finite element, finite volume. We get now a finite element approximation of that operator, a finite volume approximation of the hyperbolic. That's pretty easy because that's just a bounded operator. This is a boundary term. We don't want to go there, but that's really kind of complicated. And here's my identification problem. I want to find n max. Not only do I want to find the parameter and maybe the model, I want to find the maximum. What does that mean? Why do I want to keep my optimal n less than that? Many reasons. If you're trying to build a model for control purposes, you've got to keep your model small. Or if you don't, you get a big model and you do model reduction. But let's just try to keep it small as part of the estimation problem. How big of a model do I need to actually capture the dynamics of the system? Okay. The other thing, of course, is you know these things getting down where machine epsilon, this is less than machine epsilon, you're going to be in trouble. Or this time some important parameters is less because you're going to face the exact same problem we had in those two simple examples. So there are bounds on this. You can't have just infinitely fine mesh. So I'm pretty honest, that's just too hard for me because it's a continuous, discrete optimization problem. And part of the optimization is placing a mesh. This is a simple case, uniform mesh, but really you need to do adaptive meshing, you need to do there are people doing very complicated things. So it's an interesting optimization problem. Too hard for me. So I'm just going to simply show you what happens if we take advantage of the structure. So again, we're going to fix the flow rates, and we're going to let mu be fixed. And we're going to take the same fluid, so mu1 and mu2 are the same. And then what we're going to do is generate data for these values, because that's what would happen. That's the true model, even though that's small compared to everything else. We generate data at third points. So I do a high order finite element, finite volume method, generate data, add noise. Okay? And once I do that, I'm just take 32. Turns out you can get by much smaller because of these parameters. And I'm going to fix that. I'd really like to optimize or minimize that, but outside my capability. And we did the same thing with the model discrepancy with hyperparameters. And look, I got 8 hyperparameters. I had no really belief that we could identify these things. We're going to do a least squares, we did a maximum likelihood least squares. We're going to simplify the so we've got 2 model disturbances, one for the hot temperature, one for the cold temperature, and I'm just going to assume simple first order exponential polynomial, so it matches the dynamics. This is a decay rate, that's going to have to be negative, and we know something that it should be something similar to the decay rate we get with this, which changes with the mu, okay? So we just went at it, so can we possibly identify all 8? Forget any structure, but later we used obvious structure that we can get rid of these 2 terms, one of them, because they have to cancel each other out. That works much better, I'll tell you. But I'm going to show you what happens if you don't do that. Okay. Now remember, one of the things we want to do with the model discrepancy is not only fit the data, we want to get that model once we fit the data, and we want to use it to predict outside the calibration interval. That's sort of always the problem. Okay? So I didn't want to do anything real fancy, so first thing you do is try something you have. If it works, you go. Really, we've actually done IP opt, much more interesting, okay, to solve this constrained optimization problem. You know, it's a minimization problem. Again, n is fixed here. I'm not going to try to estimate the smallest system. But we put constraints on the heat transfer coefficient. We fixed the velocities, as I told you, and we assumed that mu could be 0, but it's small, and a disturbance could be big, but on the average, we'll take a mean, normally distributed mean 0 kind of distribution, okay? Or what we really did was, if you don't know what's there, uniform distribution. So we did the following. We did the same for the constrained optimization problem using the hyperparameters, and note, we knew that these numbers have to be negative because we know in advance the dynamics is a stable system. That's all we did, so put some bounds on it. Still in the spirit of the previous papers. So what happened? So what did we do? Well, we took initial estimate in both cases from the intervals. So initially we randomly selected an initial K1, initial K2, an initial mu, and an initial omega. And then we started the optimization problem. Did the same thing down here, okay, where we just the only information prior we used was this. We'll see how important that was. And then we ran it 500 times. I ran it a lot of times because I didn't really believe it's going to work. And what I'm going to show you, we did it 500 times, randomly generate a selection of initial condition, randomly add new noise. Think of it as a different experiment every time, noisy data. And then we got the parameter estimates, we averaged them, and saw what happened. So these are the true values. Remember, that's really there, even though it's small. That's 1, it looks like big, but that's degrees, okay. That's what, by parameterizing the model and using a little bit of information about the remaining model discrepancy, it does pretty good, right? Not bad. So we fit the parameters so well. The structured model discrepancy does, remember, there is no mu and omega in that problem. It's pretty good. The error is about the same if you look at it between those. One's biased one way and one's biased the other. The average hyperparameters, again, assuming nothing, this is what came out. Interesting. Theoretically, this plus this should be 0. Okay, it's not. But if I had imposed that, I would have reduced one of the parameters, and I could have imposed that. And we did that. The other interesting thing is look at the decay rate. Now, this is just done independently. The decay rate here, they're essentially the same. Okay? And in fact, they're pretty close to the actual decay rate for the complete PDE system, which is roughly that. So that's good news. Then the data fits, and the model prediction is the only thing that's remaining. There's the data fit. So again, remember, the red line is the hot temperature at the right end. It cools down, goes to a steady state. The cold temperature heats up and goes to a steady state. The blue and red circles are data. May not look like a lot of noise, but again, that's 90 and that's up to 2 or 3 degrees there. That's a pretty lousy temperature sensor, if you think about it, okay? And here's a comparison of all the methods. They all fit the data, okay? Really good data fits. Now I do a little bit of frequency plots, you know. So this is the actual value, this is the estimated value, and there's 2 sigma, plus or minus 2 sigma. Same thing for the structured model discrepancy. Just got different kinds of biases there. Both produce good estimates. The same thing for the other heat transfer coefficients. They're both fine, no problem. And now in this case, there is the structured model discrepancy alone doesn't know there is omega, doesn't know there is a mu. The amazing thing is the constrained optimization finds them pretty well. And the other amazing thing is, well, this lower bound's important. You know, if you've got a problem where the where the diffusion coefficient's negative, you've got a great system, right? That doesn't happen. So these are physical constraints. And so to test this, I did a lot of runs, but basically, so wait a minute, I'll just assume there is no heat transfer. I started out at 0, and that's why it stayed there a lot of times. But eventually, it settled down, and it produces a pretty good, estimate for something that the model would assume is 0. So it does, again, the structured model discrepancy doesn't. It produces the hyperparameters. What about predictions? This is the key. Both models fit the data well. And this is where things start to go out. So I went out, remember we had 60 seconds of data. We go out, and you see what happens, okay? This is a function of those parameterized discrepancy terms. And if you keep going further, the good news is the following. Both of them give you qualitatively the right answer. Well, let's keep going. We know that qualitatively, both of them have to go to a steady state. Now you see there's a drift here. The hot temperature is pretty good. So this is not really accurate physics. So you know something's wrong, it's still left. Why do I get this? That comes from not imposing that constraint. In fact, if you go back, do the same problem, and oppose that constraint, this comes very much like it just sort of locks right in. So we capture asymptotics, and we get the right parameters, and picking the parameterization of the model discrepancy turns out to be important. So, although the structured model discrepancy produces correct qualitative, the qualitative predictions, that should be quantitative, are still biased if you don't do anything, if you do the minimum amount of work. I think we need some help from the statistics community. I think you can really help here. Okay? That's the message. So I learned a lot of things, mostly that I don't know anything about these systems. But the truth is, I think there are lots of opportunities where the people that do the modeling, the people that are going to have to do the statistical parameter estimation and the optimization, come together and talk about these things would help me. The structured model discrepancy, it certainly can improve everything, okay? And it can help you get prediction outside the calibration interval by taking advantage of what you know about physics and dynamics, okay? The new thing in this is that the PD approximations, those are discrete variables, you got to consider that as part of the system identification problem. Or you can just say, nope, take as big as I want to be, get the model, and do model reduction. From a controls point of view, that sounds great, except for the fact that most of the model reduction techniques used by the controls community. There's a group of people at Virginia Tech, they're really great. They use some very good stuff. You don't retain the physical, necessarily the physical states. We'll talk about that some other time. And it all depends on the type of approximations you use. For example, the control problem, which I didn't talk about, if you go and you use straight finite elements or straight finite volumes, and if you ignore that small parameter and you do a finite dimensional model, problem's not controllable. Just not. So I can send you a paper about that. But in optimization, you won't get identifiability sometime. Thank you for your attention, and I'm trying to quit on time.